Okay, we're recording. This is going to be the review for chapter 2 on chemistry. Um, just since this is my first review for this semester, I guess I should introduce myself. I'm Nathan Chizeka. I'm a fourth semester nursing student. This is my third semester as a teaching assistant. So I basically started, I was one of the first TAs that was hired when Ameritech started using TAs and decided they were going to start teaching labs and expanding the A&P program. Yeah, I'm kind of getting on in the nursing program. I do try to really keep in mind that there's a lot of OTA students who are taking this as well. So sometimes if I give really specific nursing info, bear with me if you're an OTA student. But I also do try to make sure I consider that everybody isn't just going into nursing who's taking this class. The way that I do these, I'm not a super artistic instructor like Katie, or I'm not really an instructor, I guess I'm a TA, but I'm not super artistic. I don't like go into big drawings. The way that I learn is a lot more about condensing notes into bite-sized chunks so that if I can remember the little chunk of notes, I can think about how that applies to a question. So I'm a very process-oriented learner, and I'm a lot less visual, more I have to interact. So I end up rewriting notes a lot. So if you're the type of person who needs to write things to remember, I'm probably a good one to talk to. And outside of these reviews, if anyone ever needs anything, I really want to be helpful to people. So if you're struggling with any of your classes, I'm happy to help and give advice on how to study, what to really focus on, how to mentally just get through nursing school. I certainly have had my own struggles with getting through the Ameritech program, and we're definitely all in the program at a really interesting, difficult time. So feel free to contact me if outside of reviews if you ever need anything, or if something in my review was said and it didn't quite click, like it started to click, but then I moved on. Feel free to contact me and just be like, hey, can you, talk me through this again? Because I want to be able to do that. So and then the format of these reviews, I will review everything that is, just about everything that is in the notes. Sometimes if it's like, hey, that's just a matter of memorization, I won't tie up review time with there are a number of lines in the notes where you just need to know what that is. It's not really a process thing, or there's no way to condense it. And so sometimes I'll be like, hey, that's memorization. You need to memorize that section, memorize those definitions. But that's not common. Most of the time I try to give a breakdown of how I would write my notes, how I would approach studying it, and so on. And so I will cover everything that's in the chapters. This is not, they want me to be very clear about this. This is not just an exam review. This is a material review of what you've already learned. So I won't be giving you just what's on the exam and telling you what to study for the exam. I'll be trying to help you reinforce what you've already learned in class. And with that being said, there's also always the expectation that you've already seen this material, that it's not new. So I always want people to ask questions and interact if you need me to go over something more because it's not clear. But I won't be necessarily diving into every element and teaching it from square one. That's what your lecture classes are for. And this review is always to try to kind of just help make it click and make it stick. So there's only a couple people in here today, but if anyone has any questions, ask them now before we start. Otherwise, I'll start diving into kind of the material and going over it. Cool. Get my whiteboard open here. Move some things around. Okay. So I am starting on chapter 2. The notes open with matter, mass, and atoms. This chapter will be heavily focused on atoms and how the atoms interact with one another. So I think those 3 definitions are pretty simple. Let's really dive into the first thing we want to jump into here is the subatomic particles. So we've got 3 kinds of subatomic particles listed. You've got protons. My writing is not normally this bad. I have to use a tablet and it's very odd. So forgive me for writing like a kindergartner. We have neutrons. Oh my gosh. And we have electrons. So protons and neutrons are in the nucleus. Also, I don't spell well. Anyone who has been to a review of mine before will let you know that it's kind of a running joke to keep track of me misspelling things. I used to be very good at spelling, and then I started nursing school, and once I started trying to keep track of dozens of drugs, it just went right out the window. Electrons live on the outer valence, or the out. Let's just call it the outside. So protons. This is the way I rewrite the notes so that it's in a really small condensed little package and I can remember them. Protons have a positive charge. Electrons have a negative charge. Neutrons have no charge. Make sense so far? I mean, this is pretty 8th grade chemistry type stuff. So the function is, protons and electrons give the charge to the atom. Neutrons tend to add, the key to this is the neutrons add mass. Let me try a couple things here. Might just need more processor for this to stop writing so badly. Okay, let's see how that goes. Okay, so neutrons add mass. Protons, no, that made it worse. Giving up on that for a second. Bear with me. I'll get this right. Protons and electrons add positive or negative charge to it. Okay, so you got the idea with these notes? I'm going to erase them. Okay. So protons also give us the atomic number. Atomic number is actual, the atomic number is the number of protons in each atom of an element. So, they give a couple examples in the book. Oxygen has 8, therefore its atomic number is 8. Fluorine has 9. And generally, what any element is looking to have is elements, let's say atoms, are trying to be electrically neutral. So in order for them to be electrically neutral, the number of electrons and protons needs to match. Make sense? If a proton has 1 positive charge, to be electrically neutral, an atom needs to have 1 negative electrical charge. So therefore it needs 1 electron for every proton. The reason that this is important is because as we move along, we're going to get into bonding, and the reason that most bonds occur is that they're a way for an individual atom to neutralize their electrical charge. Because what we find is that if we allow them to just exist as they are in nature, there are many different elements that are not perfectly electrically balanced. There's one more number we need to talk about, and that's going to be the mass number. The mass number is the number of protons. Let's make this more succinct. Number of protons plus the number of electrons. No, sorry, neutrons, not electrons. That gives you your mass number. So I'm looking in the notes. Here in the notes, we should have carbon as the example, where you see its element from the periodic table. The atomic number is 6, but its atomic mass is 12, and that's because of the number of neutrons that it has as well. I'm going to move through. I'm going to skip writing the symbol for the 13 most abundant elements in the body, if you guys have that in your notes there. I haven't been to school yet to get the new notes for this semester, but I've been told that they should match really closely. So if I don't have something, speak up, or if I have something different than what you have, speak up and let me know, okay? I'm going to skip that because you can write what the symbol is for each of them. When they say symbol, they just want the abbreviation. So like oxygen's O, carbon's C, hydrogen's H, and so on. I want to move into electrons and energy levels. Electrons move in what we call the electron cloud. And that's really just these, like, we call them circular. They may or may not be perfectly circular in actuality, but we're talking, the electron cloud is, these electrons are spinning around the nucleus really fast. And if we were able to actually look at it, it would, just a few electrons would be spinning so fast, it would look like there's a cloud around the center of the nucleus, like it's a solid shell. And that's because of their attraction to protons. So as they move past the proton, they get drawn back towards it and they spin into it. But this is electrons orbiting the nucleus in energy levels. That's my abbreviated version of what's there. So let me get a new box here. The first energy level can have 2 electrons. The second and third levels can have a maximum of 8. So the way that this works is like if we were going to diagram an atom, or even if we're going to conceptually think about an atom, the first energy level, given whatever number of electrons it's going to have, the first energy level is always going to get 2. It always has to be filled before we can move to a second energy level. So the like in the case of carbon, you'd have 2 on the first level. On the second level, you can have a maximum of 8, but there's only 4 left because it's got 6 electrons. So it's going to have 4 on that second level energy shell. So you're going to put 2 on the first level. As you move out to the second level, you're going to put the 4 remaining ones on there. I'm going to try to draw this if my text allows me to do so. Oops. You got a little nucleus down here. It says our protons and neutrons. You'll have your first level. That's going to get 2. Then you'll have your second level. And that's going to get the remaining 4. If it had more, you would continue to add to the second level until you had a total number of 8 out here. If you had more than that, the remainder would go on a third level, and so on. Does that make sense? Okay, I'm getting a nodding head, that's good. Let me get my eraser, kind of erase my board, we'll move on.
In my class, we also talked about the 4th energy level.
Does it talk about a 4th energy level? Okay.
No, we wrote it in.
You wrote it in? Okay. I'm trying to think how many, the majority of things that we will work with in I think that there can be quite a bit more energy levels. Most of the elements that we deal with in the human body are going to be much lower on the, in the atomic numbers, and therefore the number of energy levels that those atoms are going to contain generally gets limited to at a max 3. There are more energy levels that do exist. I always joke when I'm doing this one that like if a chemistry professor ever saw this, he would tear his hair out, or she, because I butcher chemistry so badly. And in a past life, I had a lot of chemistry classes, but it's really about conceptualizing what's going on in the human body for what we're trying to do here, and not have a broader understanding of chemistry. And so that I think that that's why we don't get into like energy levels that are much further out than like the third. Who's your instructor that had you draw on the fourth, just so I know?
Amanda.
Okay. Yeah, Amanda has a really good grasp of this. So I will send her an email and just find out what she was getting at with that so that I understand as well why we're doing a fourth. So it's really key to know that some elements are naturally stable. They're not going to have a lot of electrical interaction, and they're going to fill their outer shell completely. So let's see, whatever is 10 on the periodic table, that element is, I could look it up, but I'm being lazy right now. That element's going to be pretty stable because there's nothing for its outer shell to interact with. It's not trying to gain an electron to fill its outer shell, and it's not trying to give anything away. And so that concept is key, because the less stable an element is, the more it's going to interact and bond to other elements, because elements are always trying to either gain an electron on their outer shell, gain however many electrons they need. Like carbon needs 4. So that's why you find carbon so reactive in so many different compounds, because it has 4 different areas where it needs to gain an electron on that outer shell. Whereas like hydrogen, is really, it's trying to give them away or share them for the most part. I'm trying to think of something else that really, what else has one that gives it, we'll get into it here in a second, but other elements, like if they only have 1 or 2 on an outer shell that has 8 that it needs to be filled, instead of filling those spots, they will give those electrons away to another element that needs that small number of electrons. So we're going to move into bonding, the way that these elements are bonding with one another, and those bonds come from them trying to stabilize themselves electrically. So ionic bonds that's where I talk about losing electrons. So let's see here. One atom loses and one atom gains. I'm going to write notes. I'm just going to stick with the text boxes. Are the text boxes better for you when I type it?
It's fine either way.
Okay. So the key with this is that, again, you've got one atom's outer shell is in need of an electron, and another atom's outer shell has too many electrons. So it's trying to get rid of that level so that it can become more stable. The ones that we have here would be good examples of how this is going to work. Let me try to draw, see if this will allow me to draw here. So you have sodium. It's 11. So you would have your nucleus here. Your first level has 2. Second level has 8. That gives you 10, but then you're going to have this third level here with just 1 electron floating on it. Now, sodium is either needs, in order for sodium to become stable, it's got to fill out that shell because the shell has its own, that third level, not shell really. That third level needs to be filled out. Otherwise, it is going to be unstable and always either picking up or dropping other electrons. So it comes across an element like chlorine. By the way, are you familiar with sodium chloride? Table salt?
Yeah, we just discussed it in class.
Okay, cool. So just drawing this again, basically for everyone's benefit. You're going to have 2 here. Eight there. That's 10. The reason these bond so easily is because this is going to have 7 out here. So sodium is like, hey, I've got 1 to give away. Chlorine's like, hey, I need to pick 1 up. So they end up, this guy ends up jumping across to here. And it will not circle around sodium for very long. It's going to spend its time circling chlorine, and therefore there's that bond. So sodium ends up giving that up, and basically it has 11 oops, let me switch back to blue here. It ends up with 11 protons in the middle. But 10 electrons circling it. Oh. That's my way of saying 10 electrons. Sorry. So do ionic bonds make sense for you? Why that works?
Yep.
Okay, cool. I think that ionic bonds are relatively straightforward to see. It visually makes sense when you start to, when you really start to draw them out here, where you're like, oh, look, like this one guy fills this out, and both of these guys have their energy levels feeling complete. Everybody wants to feel complete.
I did have a question about ionization.
Okay.
So when they break apart,
yes.
They break apart as the cation and the anion.
That's correct.
And they don't like gain their electron back. They stay as they were when they.
Yes. So ionic bonds are
giving up and lost.
Easy to break.
Okay.
And when they break apart, they will break apart in a way that allows them to have complete energy levels.
Okay.
But then they will carry a charge.
Yeah, like they're positive or negative charge.
Yes.
Okay.
But so, we say that they're seeking to be electrically neutral. But in reality, what they're really seeking to be is electrically balanced on their shells.
Okay, that makes sense.
Does that make more sense?
Yeah, that does. Thank you.
So what ends up happening, though, is that you end up, because they carry a charge, they will do things electrically. Sodium then ends up carrying a net positive charge that we write like that, meaning that it's got one more proton than it has electrons. And chlorine, I'll change my color to green, ends up being a negative charge because it has one more electron now than it has protons in the nucleus. Does that make sense?
Yeah, that makes a lot more sense. Thank you.
And a lot of times these bonds are broken down by water, which is a process we'll get into. It's called hydrolysis.
Yeah, okay, thanks.
Let me do some erasing and then we'll start on covalent bonds. Oh wait, you can do this. Ah, sweet. Forgive me for being a child and learning new things at your expense.
You're good.
Okay. So, covalent bonds. These are shared bonds between atoms. So the difference between covalent and ionic bonds. I have a relationship analogy here. Some people get it, other people don't. Ionic bonds are really unstable relationships where they're gonna like jump from bond to bond to bond to bond. They're like serial daters. Covalent bonds are like very like monogamous relationships. Once those covalent bonds form, they're a lot harder to break down because they have very equal sharing. And one of the myths that I think that we're taught as children is that like relationships should be this like give and take and perfectly balanced, but they're never perfectly balanced. Like you're going to have, even in a covalent bond, you're going to have a little bit of like sway where your electrons are spending more time around one atom or the other. And that will get us to the end of this. But keep that in mind as we kind of go through this, that there is like, you will have a larger atom sharing covalent bonds kind of with a smaller atom. But that larger atom kind of holds the power in that relationship. It wears the pants, so to speak. So let's see. The reason you see a lot of these covalent bonds are between their own atoms. Oxygen, I think, is we don't tend to think of hydrogen as H2 as commonly as we think of oxygen as like free floating in O2. I think that's one of the ones that you learn in very basic chemistry in grade or middle school. Are you with me on that one? Is that how it was kind of taught to you? Like oxygen always exists as O2. And the reason that it exists as O2 is that oxygen has, let's see if I can draw this in a way that works. It has 8 protons in the middle here. It's going to have a valence shell or a first energy level with 2. It's going to have 6 out here. Well, when it meets another oxygen that also has 8 protons and 8 total electrons, it's very easy for these two to jump across to here and circle this and make this one complete. And then as they make a lap, they will jump back across to here and make this one complete, so that you get this like figure 8 style sharing that goes on between them. Does that make sense? Where they're just going to circle back and forth. So they spend, about 50% of the time, each atom is kind of in balance.
Yeah, and that's the double covalent bond, right?
Yeah, that's going to be a double covalent bond. So I didn't draw it like perfectly appropriate, but your double covalent bond is going to be, 2 lines there.
Yeah, okay.
I was this works better on a whiteboard with markers where I'm drawing this like figure 8 thing. It didn't come out very well on here. But you also will have molecules we also will get molecules that are formed of covalent bonds as well. One of them is going to be, you know, our example here is methane. Which has CH4. So let me try to draw this. Let me get a different color. I like drawing carbon in black because like all the carbon residue, like when I grill food, is black, and it just makes sense in my brain. So you've got carbon. So carbon has 6 protons. Two on its first level, and then it's going to have 4 on the second level. For 6 total electrons, right? So then you're going to have hydrogen, and I'll draw this in a different color so that we can kind of see it. You're going to end up with 1 proton and 1 electron in 4 different places. I didn't draw that one well enough. Sorry. The black needs to connect as well because the idea is that it's picking up 2. Okay, so this guy's out here. Then we have our hydrogen here. Okay, finally, that took forever. So what you see is that because hydrogen, yes, hydrogen only has 1 proton, but its valence shell is out of, or its first energy level, its outer shell is out of balance because it really wants to have 2 electrons on that shell, right? Because that first energy level always needs to be filled with 2 electrons. So it's always seeking to pick up electrons from whatever other elements it can find. When it finds carbon, it's great because carbon has a lot of space to share, but carbon also needs to pick up 4 itself. So carbon's always like scavenging and looking for other people who are willing to share. And in methane's case, carbon finds 4 hydrogens, and it's like, look, I've got a place for all of you, and I can share with all of you. So you'll be filled out, I'll be filled out, we'll all be happy. And that's what this being drawn would look like. And you're going to have that single bond on all of them. So that moves us through covalent bonds for for an example, I mean, we also have triple covalent bonds and the example that we really give is nitrogen. It's going to be far more common to see singles and doubles. But one of the notes here that is really key at the bottom, I'm on the bottom of page 10 on my notes. Your book might be a little bit different, but let me clear this here. So a free radical is something like that hydrogen atom. It does not have a full outer energy level. And because of that, it makes it very reactive, and very reactive equals damaging in the body, in the human body. So free radicals, I'm sure that anyone watching this has seen a commercial at some point in time talking about food or shampoos even, I think, have antioxidants in them. Antioxidants, their job is they neutralize free radicals. Stop or prevent damage, really. So that's important to know, because as we go on longer, whether or not it comes up on your first exam, as you work your way through school, you begin to understand that these free radicals floating around do a number of things to damage us and can play a big role in a number of ailments. Like they have a role in creating cancers and things like that. And so at the base foundation of it, this concept of free radicals is important, because that's actually something that can be initiating a disease process. So moving from, we have these polar covalent bonds that are sharing everything between them pretty equally. I'm sorry. We had covalent bonds that share everything pretty equally. What we find is that, and this is what I was talking about when we started into covalent bonds can be, what you end up finding is that most of them are kind of polar. One of the atoms in that molecule tends to dominate the relationship and kind of hold the cards a little bit more than the others. In a non-polar bond, you get equal sharing of electrons. And you'll see, like, that's my way of like distilling that down to what do I need to know about non-polar. This is a lot of what I do with my reviews is kind of share my note-taking process and how I like to distill the facts of things out. So like if I just remember this tidbit about non-polar covalent bonds, that they have equal sharing, if I'm looking at a test question and it's talking about non-polar covalent bonds, I can bring up, they're gonna have equal sharing of electrons. And if I understand what the equal sharing means, then I can kind of break down that test question. So again, a lot of my thinking is a lot more process oriented than memorization. And I have found that through this program, generally speaking, most classes want you to be able to think through processes, not necessarily just regurgitate facts. I think that's a really hard thing for a lot of people, because they want to just be able to memorize things directly. and then have the test questions ask them what they've memorized. But what the test questions are going to seek to do throughout your programs at Ameritech is challenge you with questions that are testing your knowledge about what you've memorized. So it's better to understand the process and be able to break that down than to remember word for word every definition in the book. So that's kind of why, if you're wondering why I write notes this way, this is how my brain remembers things so that I can apply them. So polar covalent equals is not equal sharing of electrons. I don't want to do that. Okay. So we have a number of, like I drew oxygen a few moments ago and showed how that was when I was drawing that ridiculous figure 8 around both of them. Oxygen very much has equal sharing, right? Because like you need to, I need to, and we will just have those two spend equal amounts of time around both of us. So there's already a graphic depiction of what non-polar would look like. But really what is key is you get slight reactivity out of elements that have, or molecules that have polar covalent bonds. So an example would be water. H2O. I'm better at drawing with the trackpad on my computer than I am with my tablet. This is funny. So let's pick a color here. I don't know why I picked pink, but we're going to have oxygen in the middle here. It's going to have 8 protons. And it's going to have 6 electrons on the outside, so it needs to pick up 2. So oxygen binds with hydrogen very readily to create water. I drew hydrogen in red last time. I'll draw it in red again this time. It'll clash a bit. I like that. So you're going to have your outer shell, your hydrogen here. It's only going to have 1 proton in the middle. It's going to be sending that there. And that one there. So it's sharing that. But because of these, what we end up seeing is that black. So what we end up seeing is that because of these 8 protons here in the middle of oxygen, oxygen has a lot more power in this relationship. It has a lot more electrical draw for the electrons to spin around. So you end up with these electrons from hydrogen spending most of their time around the oxygen. And therefore you get these, they're sometimes getting energy, they're sometimes not. And so if we go into the relationship analogies, what you end up with is that hydrogen likes to kind of cheat on oxygen because it's just not being fulfilled by the relationship there. So in practicality, what you end up with is that 1 proton in the nucleus with a valence shell that often has nothing around it. And so you will find that in these polar bonds, hydrogen will create light bonds with other things. It's still committed to this relationship with oxygen. It's still a real bond here, but it can create light bonds with other things. And because, you know, some, let's say, just to throw a weird number on it, like 10% of the time, it still has that one electron that it can share with somebody else. And so what we end up with is that hydrogen likes to bond to itself. And this is what creates like the surface tension in water. And that's from the hydrogen atoms in the water sharing their electrons back and forth with one another, because this one would have this big oxygen over here. That's my O, oxygen. So these guys are sharing with each other because they're not getting what they need from oxygen. Does that make sense? But they're still committed to the bond with oxygen. Their real bond is with oxygen. And so surface tension can be broken very easily. It's one of the bonds that's most easily broken. Were you about to say something? No? Okay. I'm going to move on into chemical reactions. Let's see, we've been at this for a while. Do you need a break or anything? No? Okay, we can keep going. I might need a break to grab some water. Just give me 30 seconds.
Okay.
If I don't keep my door tightly closed, my dog barges in and jumps up on my lap randomly. Okay. So chemical reactions. So let's see, how do I want to note this on here? So decomposition reactions are when bonds are broken. They're broken down, they release energy. The prime example to think of with this in the body is going to be when we break down food. Food is just going to be, you know, giant amounts of foods made of molecules. And in order for us to get energy and to get the nutrients that we need, our bodies actually chemically break that down into the molecules that we need, all the way down to a molecular level. A synthesis reaction is when bonds are formed. this generally takes energy. In the book, it says requires. But if you think of it as a consuming energy, it's a little bit easier to understand. When you start thinking about things that are synthesis. And we refer to this as anabolism. All anabolism is like formation of material, building up, or building something up. Most people have heard of anabolic steroids at some point in their life. The idea behind anabolic steroids is anabolics build muscle. So that's an easy way. Maybe it's just a guy thing that I think of it like that, but that is an easy way to kind of remember anabolism. That anabolic steroids are what like bodybuilders will use to build muscle up. But they also have to lift a lot of weights and work out a lot, and therefore it requires a lot of energy to build up. So you have those two different kinds of reactions. We're going to get into a lot more about reactions, but these two, you basically, at the foundation of your chemical reactions, you either have a decomposition or a synthesis reaction. Then we're going to get into organic, and the next notes talk about organic versus inorganic. It actually just talks about inorganic, but I needed clarification on this when I was going through the course. So in my mind, organic has carbon and hydrogen. Inorganic lacks carbon and hydrogen. Is that a simple way to remember it for you? I needed to know what organic was so that inorganic would make more sense. We have a list of molecules there that are inorganic compounds. They're definitely worth getting to know. I think they do come up again later, but I'm not going to dive into it too much there because it's just a straightforward list. So we go into water. You good with these notes? I'm going to erase them. Okay. Water. So let's go through the notes on water just to break it down a little bit. Water is a solvent. A solvent decomposes things. It's reactive. Reactions can occur within it. Clean up my notes just a little bit so they make more sense to somebody else. It responds slowly to heat. So we say it has a high heat capacity. I would just say it responds slowly to changes in temperature. Because it takes a lot of energy to heat it up, but it also does take a lot of energy. It takes a while for it to release heat and drop the temperature a lot. So it's very slow to react in temperature compared to a number of other things. And maybe one of the key things to know about water is that it is a polar covalent bond. We have in the notes that it's a polar molecule, But if you think of it as a polar covalent bond, you start to, if you can remember the things from earlier, it makes it a little more sense, for me at least, to think of it as a polar covalent bond and all the things that go along with that. And what that means is that, really, there are, because it's polar, it has a lot more electrical activity than other molecules. It will allow for a lot more electrical activity and bonding than other molecules. So the next thing that gets people is we're going to talk about pH. pH. This is how acidic or basic, let's say alkaline, in parentheses, basic, something, basic A substances. Open up my text box a little bit here. Okay, so pH is a measure of how do I want to phrase it? It's really a measure of hydrogen ions. The more hydrogen ions is more acidic. The trick with pH is that because it has more hydrogen ions, but it's measured using a weird logarithmic scale, and I'm a bit older, and so my logarithm math is like way behind me. Basically, all you need to know is that a smaller number of pH means that it's more acidic. So the scale, let's add another note here. pH scale ranges from 0 to 14, with 7 being neutral. 0 is most acidic. 14 is most alkaline. And what we find is, like, the human body does not like to get away from 7 in most cases. We like to be pretty neutral. Our blood likes to be, it's a very important one to know. Memorize it now in your first semester, and it will make everything, if you're in the nursing program, it will make everything in life easier as you go on. I'm not sure if you're in nursing or OTA, but which one are you in?
Nursing.
Nursing, okay. It definitely, in your third semester, will start to come into play, and it doesn't go away. You're constantly looking at acid-base balances in your patients. And I have a good friend who's an occupational therapist. I need to ask her how much this affects their work as well, so that I can help with OTA students. But either way, memorizing this number of 7.35 to 7.45 now in your first semester will go a long way as you progress through your schooling here. That's the pH of blood. That's where it really likes to be. And that's a fairly neutral number. So let's see. Key to know, like I was saying earlier, is that the more hydrogen ions that are in a concentration or a solution, the more acidic that solution will be. And then a base removes hydrogen ions and replaces the hydrogen with hydroxyl, which is, the compound is OH minus. And what that does is it makes it more alkaline and the pH will rise. And the key to neutralizing pHs, in the human body, we have a number of these, but we also have chemicals that can do this, is called a buffer. Anything that neutralizes the pH of a solution is called a buffer. I'll put that in a text box. Chemical that works to neutralize pH. Baking soda, a lot of your antacids, like Tums, will work to neutralize stomach acid. And we also secrete a natural or a buffer that's made inside our systems that's called bicarbonate juice, which is a really gross word for some reason. Like calling it juice is weird to me. It's like the word moist. So, I mean, that kind of covers key things about pH, just boiling it down to a nutshell there. Do you have questions about any of the pH stuff?
No, I don't.
Okay, cool. There's another note here about organic compounds. I kind of went over that earlier. I think covering organic versus inorganic at the same time makes more sense to me, and so that's why I do it there. Let's see how far we want to go here. Okay, I'm going to go to as far as nucleic acids today. And then we'll cover that a little bit more next week. Have you guys done all of chapter 2 already?
No, my class has only gotten up to the pH scale. Like, we haven't even learned the pH scale.
Okay, you know what? Then I'm not going to go further ahead because I want to reinforce what you've learned. I don't want to confuse it with my way of simplifying notes for something you haven't learned yet. Won't make sense if we go further.
Yeah.
Does that work for you?
Yeah, that's perfect. Thank you.
Okay. Allie, are you still there? Do you need to go over anything further today?
Yeah, I'm still here. There's just a few questions that I had, but I can talk to you about them later if you want me to.
Yeah, why don't you just message me later and I'll get with you and we can go over that and the cellular stuff that you need to know for your class.
Okay.
Okay, cool. Thanks for coming, Amber. I appreciate it.
Yeah, thank you.
All right, I am going to kind of shut it down for today then. Let's see, stop sharing. Stop recording.